Assalamualaikum warahmatullahi wabarakatuh, and hi to my fellow panels. My name is Amirul Wafiy bin RASHIDI. My MATRIC number is B09191092, and I am from BMMV Section 1/1. For my title for PSM is Simulation of Lift-Type Spherical in-Pipe Turbine at Various Velocities and Pressure Condition. Okay. For chapter 1, for introduction, first one is background. Hydropower is a mature and cost-competitive renewable energy source that plays a critical part in the electricity mix of the 21st century, accounting for over 16% of global electricity output and around 85% of global renewable electricity. Hydropower capacity, which is used in over 160 nations, is constantly increasing. Hydroelectricity has a number of advantages over other power sources, including high reliability, proven technology, high efficiency, cheap operating and maintenance costs, flexibility, and a big storage capacity. As you can see in this picture, this is a hydropower plant. Second one for the problem statement. Number 1, the design features of the turbine can be studied in order to maintain the performance of in-pipe turbine. Second, according to research on turbine design, for fluid flow, number of blades, pitch angle, type of lift-type turbine, physical model for blade, and aspect ratio influence the pressure and velocity reaching the in-pipe turbine. Third, a bad design will result in low output velocity and pressure. And last one, the water distribution channel will be slower and less efficient to utilize. Okay, for research objective, we have two objectives. The first one, to analyze the effect of lift-type water turbine in pipeline based on outlet pressure and velocity. Last one, to perform computational simulation of lift-type in-pipe water turbine. Okay, for the scope of research, we have 4 scope research, which is number 1, to carry out the efficiency of the lift-type in-pipe water turbine in the pipeline. Second, find the best parameter for the turbine based on the number of blades, pitch angle, and the physical model. Create a 3D drawing and simulate it using the parameters provided. And number 4, investigate the difference between lift-type water turbine and drag-type water turbine. That's all from chapter 1. Okay, for chapter 2, which is literature review. In this chapter, we have type of water turbine, in-pipe water turbine, flow of water, design lift-type turbine, vertical axis lift-based pipe turbine, difference between lift and drag-type water turbine, and simulation. Okay, for the water turbine, we have 2 types of water turbine, which is reaction water turbine and impulsive water turbine. For the reaction water turbine, it is the combined action of pressure and moving water generates power in reaction water turbine. For the impulsive water turbine, the impulse turbine uses just water's kinetic energy, and then the velocity of a high pressure water jet is changed by the impulsive water turbine. That is the example of the impulsive water turbine. Next, in-pipe water turbine. The system operates by utilizing gravity-driven water flow. The turbine's aerodynamic blades use the pressure of moving water instead of obstructing it as a traditional hydroelectric turbine would. The technology of a wind turbine is used to create hydropower in a pipe. The best part is that unlike a hydropower facility on a dam river, this concept has no negative environmental impact. Gravity-based water system can provide 10 to 15% of a region's electricity demand. As you can see, in this picture, this is the example of in-pipe water turbine. Okay, next for the flow of water, we have 2 types, which is first one is laminar flow and then turbulent flow. For the laminar flow, A laminar flow is defined as fluid motion that is smooth and streamlined. Laminar flow occurs when the parameters of the fluid at each point of the flow stay constant, such as velocity and pressure. It is most commonly seen in viscous or low velocity fluids. The fluids layers in laminar flow stay parallel to each other without missing or affecting the root of the adjacent layers if the flow path is divided into numerous infinite levels. For the turbulent flow is a typical event that can be seen in river flows, smoke escaping from exhaust pipe, or even experienced in aircraft during turbulence. The irregularity or obstacle in the path of the fluid flow causes the turbulent effect. Okay, that's for the flow of water. Okay, for the design lift type turbine, to create the best design of lift type water turbine, we make a research to give the best design for lift type water turbine. Four aspect we research is, the first one is number of blade, pitch angle, physical model for blade, and type of water turbine. Okay, for the type of water turbine, a spherical water turbine was chosen. Why a spherical water turbine was chosen? This is because a spherical turbine capable of unidirectional rotation under reversible flow circumstances is described for any fluid type at any depth or elevation. A spherical turbine is helpful because it is always symmetrical to flow by design, which is especially effective in metropolitan setting with all structure and in flat location with variable winds such as Patagonia. Furthermore, a spherical frame is probably the strongest and most reliable three-dimensional frame in mechanical engineering. For the number of blade, 4 number of blade was chosen. This is because the number of blade has an impact on the turbine performance. The 3-bladed turbine had a substantially lower efficiency than the 1 and 2-blade turbine. But based on the research, 4 number of blades has the average point based on the head loss, torque, power, and efficiency. And then for the physical model for blade, when comparing the torque values of single blades under different airfoil in figure, as you can see in this picture, it can be seen that the maximum torque value of NACA 0015 airfoil is significantly higher than that of the other 3 airfoil, and its minimum value is also smaller. Torque value generated by NACA 4415 and NASAN LF0416 are close to each other, and when the phase degree is 120E to 70E. Torque value of all airfoil will first increase and then decrease with all of them. As you can see in this picture, this is the picture of NACA 0015, which has been chosen for the physical model for blade. And this is the picture of NACA 0015, have the high efficiency compared to the other model. Okay, for the pitch angle, small negative pitch angle were shown to boost performance with the maximum power coefficient being obtained. Positive pitch angle, on the other hand, were found to reduce overall efficiency. It's vital to remember that excessive pitch angle are bad for performance and can lead to a surf load imbalance between the blade. As you can see in this picture, the left side is a positive pitch angle and the right side is the negative pitch angle. And for the pitch angle, we have choose the positive pitch angle based on the research. And then for the angle of the blade, based on the graph, 60 degree of angle have the best value based on the Coulomb factor and friction factor. Okay, for the vertical axis lift-based pipe turbine, Roloff pipe turbine have a spherical shape that allows them to fit into a pipe. The turbine shaft or axis of rotation is always perpendicular to the flow, independent of its direction, and hence rotates in the same direction with the same angular velocity. The turbine blades are attached to the bottom and top hubs and sweep the spheres outside imaginary surface area helically. Okay. Next, for the difference between lift and drag type water turbine. For the lift type turbine, the turbine starter difficulty with a wide diameter and high flow rate. For the drag type, for starter, it is easy for drag type to move. And then for the lift type turbine, turbine's pressure loss grow in a small value. And then for the drag type, the turbine pressure loss grow dramatically with flow velocity. In other words, the lift type turbine have the high efficiency, but the drag type, for the starting, it is slow to move the blade. In this picture, for the left side, this is a lift type water turbine, and the right side this is the drag type water turbine. Okay, for the last one, for the simulation, in this study, CFD simulation are used to model the operation of turbines with varying geometries and operating circumstances. The geometrical model of the turbine was created using CAD software. SolidWorks 2018 was used to generate the geometrical model of the turbine. The final model was imported into ICM CFD 2018 for mesh generation. That's all from chapter 2. Okay, for chapter 3, which is methodology, for the first one is flowchart. Okay, we start and then we do the literature review. Next, design blade according to research. Next, create 3D model. And then boundary and meshing. And then input data. Next, equation. And then we do the simulation. After we do the simulation, we get the result validation. If the result validation is valid, we move to discuss result obtained. If the result validation does not valid, we do the different setup and then we do again for the simulation. After they discuss result obtained, and then we finish and then we get the data. For the modeling, design of lift-type turbine was designed in SolidWorks 2020. Every parameter of the lift-type turbine was designed based on literature review, which is the number of blade, physical model, and pitch angle. As you can see in this picture, this is the design for the lift-type water turbine, which is designed in SolidWorks 2020. For meshing, as suggested in literature, unstructured tetrahedral elements were used for the rotating domain meshing because of more complex geometry to be captured by the mesh and also to allow automatic meshing for all the upcoming geometry modification. In order to determine the minimum grid size or mesh resolution required to resolve the boundary layer and the mean flow features, a grid independent study was conducted. For the boundary condition, ANSYS Workbench 2022 R1 mechanical was used for numerical simulation. In transition mode, the simulation will run. Due to the existing non-symmetrical plane along the pipe size, a comprehensive geometrical model is developed and simulated, as in a recent study on in-pipe turbine. As for the result, the detailed design was made from the modeling. As you can see in this picture, the detailed design was made from the previous design and then made the detailed design in the SolidWorks 2020. For the new configuration, a new parameter was added when the model was enlarged. The diameter of the pipe and various combinations were all considered in the previous chapter. It has 6 variables, which is exchange value of pressure and velocity. For the velocity, it's starting with 16.27 meter per second, 15.21 meter per second, next 13.37 meter per second, next 15.94 meter per second, 15.31 meter per second, and 12.04 meter per second. For the parameter and project work, for the diameter of pipe, we use 40 inch, which is 1 meter for the diameter. For the fluid, of course, we use water. And then the change, which is the pressure and velocity, is keep changing, which is we starting with velocity 16.27 meter per second, and for the pressure 367,138 Pascal. For the computational fluid dynamic new mesh model, the physics choice is set to CFD and linear element order, since the goal is to compute the kind of fluid flow. When it comes to getting the element size smaller and the mesh finer, the element size is crucial. Each arrangement element size was set. Okay, that's all from chapter 3. Okay, for chapter 4, which is result and discussion. For result of turbine final design, as you can see in this picture, this is the top view of the water turbine, this is the side view, and this is the isometric view. Okay, that's all from chapter 4. Okay, for PSM2, we will be continue do our project to run the simulation and do the research and get the data. Okay, that's all from me. Thank you.